Hello everyone. Today we'll be talking about bits and bytes in a computer system. Let us first understand the representation of data. In this lecture, we will understand how an integer value or a floating value or a character or strings are represented in memory. Let us start with an integer value. In real world, humans are familiar with the decimal number system. And before talking about number system, I would like to point out a slight difference between a digit and a number. When there is a single number involved or a single digit, look at this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are digits because they are single. But if you combine two or more than two digits, you will get a decimal number. Like 1 and 0 are two digits and it gives us a number that is 10. Understand this. But computer does not understand decimal number. So what do? We convert decimal number to binary because computers are familiar with the binary number system. The same goes for digit and number here also. If we are talking about 0 or 1, then we are considering bit or binary digit. If you combine these two digits, then we get a binary number. For 2-bit system, 0001, 1011 are binary numbers. So how does a computer store information then? A computer stores all of the information in the form of bits and bytes. For example, let us suppose that we want to store a number 14 in our memory. That is, number is equal to 14. Since 14 is a decimal number, we first need to convert it to binary number system. If you do so, you will get 14 in decimal is equivalent to 1110 in binary. So how do you represent this 1110 in binary? Like this. Since 14 is an integer value, it requires 16 bits. 1 bit, 2 bit, 3 bit, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Total 16 bits. But 14 only requires 4 bits, 1, 2, 3 and 4. These 4 bits are placed over the LSB side of the 16 bits. 1, 2, 3 and 4 here. 1110. And all the remaining spaces are filled with zeros. Okay, all the remaining spaces are filled with zeros. And notice here the 0 at the MSB side is highlighted. Why did I do so? Let us understand that. So 14 is represented in 16 bits like this. So how do you represent a minus 14 in these 16 bits? That's a common problem. Minus 14 is also an integer. So we do it like this. If you place 1 in this MSB place, it represents that this number we are representing over here is a negative number. So plus 14 means the MSB value will have 0, minus 14 means the MSB value will have 1. So if you represent positive number like this, negative number like this, so how do you represent 0 then? The answer is simple, like this. Now let us consider a little bit about byte. 1 byte is equivalent to 8 bits. To store an integer, C program requires 2 bytes, 16 bits of memory, as shown above. So, the largest number that can be stored in 16 bits of memory can be calculated as shown here. 2 raised to 16 is equivalent to 65,536, and if you subtract 1 from it, you will give 65,535. This is the largest integer number that can be stored in 16 bits of memory. How? Let me explain a little bit about it. Since here are 16 empty places, look at these places, there are 16 places for a digit to be, and each places can have either 0 or 1. This place can be filled with 0 or 1, this place can be filled with 0 or 1, and all these places can be filled with either 0 or 1. Therefore 2 raised to 16 gives us 65,536, and if you subtract it with 1, you get 65,535. Why did I subtract it from 1? Because we are considering 0 also. This is also an integer. Okay, this 0 is also an integer, that's why we are subtracting it to consider 0. Hence 65,535 is the largest integer number that can be stored in 16 bits of memory. What I mean to say is, if you convert this number 65,535 to binary number, you will place all these values over here, and if you try to convert, let's say greater than 65,535, let's say 65,536, if you convert that 65,536 in decimal to binary, that number won't be able to fill up these places. It will require more spaces. Let me show you an example. 65,535 in binary. Okay, let's see. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16. Okay, 16 bits. And what if I try to store 65536? Let's see then. Here 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 and 17. But there are not 17 places here. We only have 16 places. Okay, that's why it is not possible for us to store a great number greater than 65,535 in these 16 bits of memory. Remember that. Now let us talk a little bit about RAM. In our common home PC, 4 GB is a common memory space of our RAM. What does that mean? It means you have 4 into 1024 MB available, or if you convert MB into KB, you multiply it by 1024 once again. And if you want to convert if you want to convert KB into bytes, you have to multiply it by 1024 once again. And if you want to convert it to bits, you have to multiply it by 8. So when you convert 4 GB into bits, you will get 4 into 1024 into 1024 into 1024 into 8. This is the maximum number of these yellow boxes available in your 4 GB RAM, okay, to store a bit. So that's all about an integer number. So how does a computer represent a floating point number or a decimal point number? For example, 1.7. How do you represent it? Well, there are lots of calculation involved here, which is the scope of digital logic. If you want to learn more about it, you can search for single precision format and double precision format in digital logic. But let me give you a gist here. 1.7 is also equivalent to 17 to power 10 power minus 1. 17 into 10 power minus 1, where 17 here is a magnitude and minus 1 here is an exponent. And look at these numbers. 17 is an integer, minus 1 is also an integer, and we already know how to represent an integer in memory. So we have to do a little bit of calculation involved, and you will get up to an integer value, and those integer value could be represented here in SEM format. So what is SEM? S stands for sign, E for exponent, and M for magnitude. This S is similar to this 0 and 1. If you are talking about plus 1.7, you will write here 0. If you are talking about minus 1.7, this place will be filled with 1. And the remaining places is reserved for exponent and the magnitude. There are two ways to store floating point number in C program, using float and double. Float requires 32 bits. Okay, remember that float requires 32 bits. Integer required 16 bits. Now float requires 32 bits. Among these 42 bits, first bit is for sign. Okay, 0 and 1. This. And the remaining 31 bits is for exponent and magnitude. Similarly, for double, you will require 64 bits. A number represented as double will require 64 bits to save. If there is a number that is very large, you can use a float. You can use double instead of float. Okay, for a greater decimal point number. And among these 64 bits, first bit is for sign, and the remaining 63 bits is for exponent and the magnitude. Once again, if you want to learn more about it, you can search for single precision format and double precision format in digital logic. But this is more than enough for us to learn in C program. So we talked about integer number, a floating point number, and now it's time for us to understand character. How are characters represented in our memory? If you look at this table, these values are almost taken from the, seems like they are always taken from the, they are all taken from the keyboards. Look at your keyboard and look at these values. Are they same? Almost, yes. Now let us understand it. This is called Ascii characters. Okay, all over the world we follow a standard format called Ascii character set, and we don't need to know much about it. Let's focus on what is required for this course only. We want to understand this portion of uppercase layer, uppercase letters. So uppercase characters from A to Z are represented in decimal as 65 to 90. So uppercase A character is represented by a decimal number 65. Uppercase B is represented by decimal number 66. So if you convert this 65 as a decimal number, if you convert this into a binary number, that number of bits is considered to be A. When you press A in your keyboard, that number of bits are being transferred from keyboard to your memory. Okay. When you press B, 66 is going. 66 value is going from your keyboard to your buffer. And these are about the uppercase letters, and here are the lowercase letters we are more concerned about. Look at these values. Lowercase a has a decimal value of 97, lowercase b has a value of 98, and the list goes on serially. Okay, you have to remember the starting point, and you can remember all those. The starting point for uppercase a is 65 and the lowercase a is 97. And if you notice here, you will see the difference of 32. 65 plus 32 is equal to 97. 66 plus 32 is equal to 98. 67 plus 32 is equal to 99, and the list goes on. So why is 32 necessary? Whenever you are trying to convert uppercase letter to lowercase letter or lowercase letter to uppercase letter, that value 32 is going to be a vital one. So remember, 32 is very important for us. Okay, when you convert from uppercase to lowercase, you just add plus 32 in its value. And when you convert from lowercase to uppercase, you just subtract 32 from it. Okay. And next thing we are concerned about is this null. This null value has zero decimal value. This null, we will be talking about this null in strings. Okay. When we will be talking about arrays and strings, this and null we will discuss about it in there. Let us understand the problem. Do you know the difference between a character and a string? We just learned about integer, float and character, but what is the difference between a character and a string? Do you know it? And do these two represent the same? 1 and 1 are the same? Let us understand these two questions through this one. So, an integer number in C is stored like this. Okay, 17. The value of A is 17. The value of B is 1.7, and the value of CH is A. Okay, this is an integer number, this is a floating point number, and this is a character. Notice here a quotation mark. A single quotation mark or double quotation mark is used to represent a character, but for convenience I use single quotation marks for characters. And this is considered a string. Okay, remember back when I said there is a difference between a digit and a number. The same case applies here. If you are talking about a single character, it is a character. Okay, but if you are considering the collection of character, it is a string. For example, here this is my name, and here you can see collection of characters. Even this space is also a character. Remember it. I use single quotation mark to represent a character and double quotation mark to represent a string. but that's not compulsory. You can use either one. That's for my own convenient purpose. So this is an integer, this is a float, this is a character, and this is a string. Now let's come back to these questions. Are they same? Obviously not. Since there is a single quotation mark, it is character. Okay, this is a character. We say it a numeric character, and this is considered a integer. This is an integer value, this is a character value. There is a difference. Okay, this was for today. Next we will be talking about memories in our next lecture. Thank you for watching.